All right, so I want to just step back a second and overlap a couple slides with last Friday because I kind of started rushing through it. And the most important thing is the linear change of variables when you're integrating. So if you've got a function here, so the whole idea is you want to compute these definite integrals. In order to compute them, you need to find an indefinite integral. So in other words, you need to find an antiderivative for f. That's what you really need. And then you're going to evaluate it at b and then subtract the evaluation at a. So you've got to find an antiderivative for f. But now you've got, it's not just f of x, it's f of some linear function of x. And the idea here is to get rid of that thing inside you're composing f with. So you're composing f with a linear function. How to get rid of that linear function so you just have something f of a variable, d that variable, say f of y, dy. And this is how you do it. You set y equal to mx plus c. You change the limits of integration to reflect that, and so instead of, you take f of y, and if x is equal to a, then y is equal to ma plus c. And when x is equal to b, you have y is equal to mb plus c, so that has to change. And you take a 1 over m. Remember where that 1 over m came from? Well, it's on the slide. It comes from replacing dx by dy. So dx, dy divided by dx, that's the derivative of this inner function, the function of y given x. And so the derivative of that thing is just m. And so when you make the substitution from dx to dy, you wind up dividing by m. And that division can come out because of linearity of the integral. All right, so the example we used was this, the sine of 2x dx. Well, if y is equal to 2x, then dy over dx is 2. And so dy is equal to 2 times dx, or dx is equal to dy divided by 2. And so that's where the divided by 2 comes out, and that changes to dy. And you have sine of y, and this goes from 0 to pi now, because as x goes from 0 to pi over 2, 2x is going from 0 to pi. And let's just finish this off. So how do we do this? Well, what's the antiderivative? I'll write this over here. What's the antiderivative of sine x? Say, I don't know, sine x dx is negative cosine x plus the constant, which is going to disappear. Oops. Back up. There we go. Okay, so this is going to equal 1/2 negative cosine x evaluated at pi and 0. And you don't have to put the plus c, because the plus c is just going to cancel itself out when you take this difference. So what do we have here? This is 1/2. So negative cosine, I'll just write it out in full gory detail, minus cosine of pi minus a negative cosine of 0. Does that look lovely? Okay. So what's cosine of pi? The x coordinate. Negative 1. Okay. And cosine of 0 is 1. So this is going to be 1/2 of a minus a negative 1 is 1. And then those two minuses cancel out, and I'm just left with 1, so that's 1 plus 1. And so that's 2 times 1/2, and that's equal to 1. So take sine of 2x the area under the curve from 0 to pi over 2 is exactly unit area. The area is exactly 1. Yes, question.
So for when we get on the lower portion, we actually have the we completed the integration. And it has to be a negative cosine x. Is that like really negative cosine y, or do we go back to the original variable? Or am I overthinking that?
No, you're not overthinking that. You know, actually, it doesn't.
Or is it just a variable?
It doesn't really matter. It's a dummy variable, and it's assumed that it's x going from pi to 0. But you're right. It actually is. It's more consistent to keep this as y, because we did change the variable to y, and so that's what I'm actually using here. So yeah, you're right. So let's change that to y. And it's the y that you're evaluating a pi, and you're setting y equal to pi and then y equal to 0. That looks a little nicer, doesn't it? That looks better. Good. Other questions? Okay.
And you would take the derivative in the stated goal.
What was the stated goal? I'll draw a picture. So, sine of 2x looks like this. You know, sine of x has period pi. Well, sine of 2x has period pi over 2. I'm sorry, sine of x has period 2 pi, so sine of 2x has period pi. We're integrating that function from 0 to pi over 2, so that area is exactly. Geometrically, that's what we're doing. And does that answer your question? Okay. All right. So we need to know some indefinite integrals so that we can actually get rid of the integration sign. You know, replace them with this very simple difference. And so we write an indefinite integral like this, also called an antiderivative. So this looks like an integral, but there are no limits. So it's called an indefinite integral. And all this stands for is some function whose derivative is f. So g prime of x is equal to f of x. So we take that as our antiderivative. So here is the connection. If you actually fix the left limit and vary the right limit, you get a function, and let the right limit be x. You get a function of the right limit, and you integrate f. That actually gives you, up to an additive constant, that gives you the antiderivative. Okay. And going the other way, to take a definite integral from a to b of f, you take the antiderivative and just evaluate it at b and subtract, and evaluate it at a and subtract those two. So really, you can forget the pink, this purple thing. Remember the yellow, because we're only going to be dealing with definite integrals. So remember the yellow. You need to find the antiderivative, and then you just evaluate it at the edges of the integral and subtract. Okay, and that gives you. This is the fundamental theorem of calculus. So it gives you the definite integral. This is how you get rid of the integral sign. Did I tell you where the integral sign, what the integral sign actually is?
Yes.
Okay, yeah. It's an old-timey S. It probably comes from the word sum, because the integral is really sort of a continuous sum. Okay. All right, so here are some common indefinite integrals or antiderivatives, and we've gone through this slide before. You can pick it up as you wish. All right. So let's do this example. This is, I think, where we left it last time. I'm going to integrate from 0 to pi of e to the ix dx. I here is the imaginary unit. Okay? But everything I said about linear change of variables, the actual m, the m that we use, doesn't have to be real. It works for any m. So think I here as just any constant. All the same rules apply. So we can actually do this, and well, we're going to do it in two different ways. We are going to first take e to the ix and use Euler's formula and replace it with cosine x plus I sine x. So if we do that, great. We do that we replace that inside. Then we use linearity of the integral, so we can move the integral inside the sum. We can distribute it across the sum, and we can pull constants outside the integral. So we move the integral inside to cosine x dx, and inside to sine x dx, and we pull the I outside, because I is just a constant. It happens to be imaginary, but that's fine. Everything still works. So the antiderivative of cosine is what? See the previous slide, sine. So here, to replace this, so now we've got it in a simple form where we can look up in the table what it is, and that's sine of x. So we evaluated pi minus 0, and then this is going to be, the antiderivative of that is, as from the previous slide, was minus cosine. So we can evaluate minus cosine from pi to 0, but we'll pull the minus sign out again. So that's where that minus sign comes from. It's because this is a minus cosine of x. So evaluating pi and 0, well, sine of 0 and sine of pi are both 0. And cosine, well, we just did this, didn't we? So this is 2. Well, it's negative. This is negative 2, but we negate it again, and so we wind up with 2i. So that's the answer. Questions?
Why do we move? Oh, never mind.
All right. So that's one way of doing it. Okay. You can just take the complex exponential and express it as trig functions of x. The other way of doing it is to use linear change variables, where now you set y is equal to ix. And in this case, we use the linear change of variables formula, and e to the ix now becomes e to the y. And here, the constant, the coefficient is I. So you get a 1 over I outside. And as x goes from 0 to pi, ix is going to go from I times 0 to I times pi. Okay? And then there's the dy. All right? So I did this on Friday. 1 over I is equal to minus I. Okay? That's just worth just remembering if you can. And if not, well, ask someone. 1 over I is equal to minus I. Okay? So change that. And now we've got this. Well, now we can use the fundamental theorem of calculus and say, well, what is the antiderivative of e to the y? It's just e to the y. It's its own antiderivative. So we get e to the y evaluated at I pi minus the evaluation at 0. All that times a minus I. So e to the I pi. What is e to the I pi? So that's e to the I 0, e to the I pi over 2, e to the I pi. It just goes around the unit circle, so that's a minus 1 in a complex plane. This is actually a famous equation. Because it uses all the constants, all the important constants of mathematics in one equation. Okay, e to the I pi is minus 1. That's minus 1. E to the 0 is 1. So I get minus I times a minus 2. I get 2i. So you could do it either way. You might wonder about this. So I'm going from 0 to I times pi. You usually think of integration as going along the real line. Okay, but here it's not going along the real line anymore. It's taking a path from 0 up to I pi. This is the imaginary axis. The path is now here. You're integrating along this path. And so dy, the little path increment that you get, the infinitesimal path the path increment, is actually purely imaginary at this point. It's going up this way. This is called a path interval in the complex plane. And that's neither here nor there, really, because you can just apply the same rules you apply for integrating along the real line. So the same rules apply here. Incidentally, you can alter this path. If you have a function that's defined everywhere for the whole complex numbers, which the exponential is, you can vary this path, and you can take any route you want, as long as you start at 0 and end up at I pi. If you integrate along that curved path, you'll get this exact same value. You get 2I. So the actual interval doesn't depend on which path you take, interesting. As long as it starts and ends at the same place, that's you. All you're doing is you just take the endpoint, that function at the endpoint, minus the function at the beginning. But again, that's neither here nor there. Just apply the rules that you want. All right. Great. So now we're going to get on to back to waves. And today really is about the superposition principle. The fact that you can superimpose simple functions together. You can add them together to get complex functions. And to start, we'll use this example from calculus, power series. So from calculus, we know that certain continuous functions can be expanded into an infinite series of the following form. So f of x, you take some constant plus another constant times x plus another constant times x squared, and you add these together and you have increasing powers of x with certain constant coefficients outside. This has a name, right, this series? What's it called? Can you remember? It's been a long time. Series. It's a power series. I thought I heard it. What was it? Maclaurin series? No? Okay. There's another name that's a little more general. Taylor series? Do you remember Taylor series? An example of a Taylor series. The Taylor series centered at 0, which has the name Maclaurin series for reasons I don't know. And so you can write this more compactly as the sum of from n equals 0 to infinity, so it's an infinite sum of just some series of coefficients times simple powers of x. So what we're doing is we are decomposing f into a sum of simple functions, or a linear combination of simple functions, powers of x. And C sub n gives you sort of how much weight are we giving to x sub n in this decomposition. So if C sub n is really small, then this term doesn't contribute very much. But if C sub n is large, we're contributing, x sub n really contributes a lot to the sum. The idea is that to find these coefficients C sub n, and when we do, this function is completely determined by the C sub n. So all the information about the function can be transferred into the values for these coefficients, and vice versa. If you have all these coefficients laid out, then that determines the function. So the function determines the coefficients, and the coefficients determine the function. So the coefficients are It's sort of equivalent to knowing the function. But the advantage of knowing the coefficients is these are discrete quantities, one for each integer starting at 0. And so sometimes the discrete quantities are easier to work with. In particular, you can approximate the function by just taking the first few terms, some finite number of terms here, and just take that as a good approximation for the function. So the function is fairly easily well approximated by just taking maybe the first, 5 terms or 10 terms, and ignoring the rest, ignoring the tail. Because these terms the actual values of these terms have to diminish to 0 as we get to infinity, otherwise this sum doesn't converge. So you need that. All right, so this was a Maclaurin series. Here is the way you get the coefficients from the function. So we're going in two directions. We're going from the function to the coefficients. Here we went from the coefficients to the function. So if we know the coefficients, we just add them up times the powers of x and we get the function. Here's how you get the coefficients from the function. You're going in the other direction. Take the function f of x, differentiate it n times. So this is c sub n. You take the function f, you take its derivative, and then you take the derivative of that, and then the derivative of that. Keep doing that n times. Then evaluate, you'll get a function of x when you do that. Evaluate that function at x equals 0. That gives you a real number, and then you just divide by n factorial. So that's the standard formula to get each coefficient of the power series. That gives you c sub n. So if you do this for the exponential function, so f of x is e to the x. Well, what's the derivative of e to the x? It's just e to the x. So no matter how many times you differentiate e to the x, you're still going to get e to the x. So when you evaluate e to the x at x equals 0, you get e to the 0, which is what? Which is 1. So each coefficient of the power series for the exponential function, e to the x, is just 1 over n factorial. So here's the complete power series. It's 1, which is 1 over 0 factorial, plus x divided by 1 factorial, which is just 1. X squared over 2 factorial plus x cubed over 3 factorial, which is 6, plus x to the 4th over 4 factorial, which is 24, and so forth. So that is the actual Maclaurin series for e to the x. And the idea is that we're just taking e to the x and decomposing it as a sum of very simple functions, just integral powers of x. All right. And in fact, this actually works. X doesn't have to be real here. This gives you the power series for e to the x for any complex number x. So we expanded the definition of the exponential function to the complex plane. We did that on Friday. You have the same series that works for the entire complex planes. All right, but let's stick to the real line for a second. And let's evaluate, let's truncate this sum to just take the first finite number of some finite number of terms. So if we only take 3 terms of this sum, and we graph the function, so 1 plus x squared over 2, we get this green line here. If we take 2 more terms in and graph the function for the first 5 terms, we get this green line. We take 7 terms, we get this green line. Here we're going from x equals 0 to 6. 9 terms, we get that line. Notice the actual exponential function is the blue line. And as we take more and more terms in the approximation, we're getting closer and closer to it. At least in this range, from 0 to 6. Okay. These approximations get worse and worse the further out you go from 0. The further out x is from 0 in either direction. But if you include enough terms, for any particular x, if you include enough terms, it will eventually approach the function. It will eventually approach the exponential function. All right. So we're going to do this now with waves, with wave functions, and this is called Fourier theory. So it's the mathematical tools to implement the ideas behind the superposition principle. For periodic functions, waves that are periodic, we will decompose them into a discrete sum, an infinite sum, but it's a discrete sum called its Fourier series with coefficients. And this is, so in some ways this is analogous to the power series. But the power series is really only good for continuous functions. Here, the Fourier series we're going to use only applies to periodic functions, but these functions may be discontinuous. And then we'll talk about aperiodic waves. So an aperiodic wave might be a pulse, just one pulse that's sent along, and it might have a particular shape. Well, we're going to apply the same superposition to the pulse, and we're going to decompose it into component frequencies. For the periodic wave, these frequencies are discrete. So they're going to be discrete multiples of a fundamental frequency. For an aperiodic wave, the frequencies that we decompose that wave into will lie in some continuous spectrum. And that's because it's aperiodic, really. That's the reason. So we get a continuous spectrum of frequencies. And to get that spectrum, we use what's called the Fourier transform. So we'll describe all of it. So think of Fourier theory as being in two pieces. Fourier analysis is you start with some complicated wave, and then you decompose it into its constituent simple sine waves. So you can always express a complicated wave, almost always, express a complicated wave as a sum, as a combination of simple sinusoidal waves of various frequencies. Fourier analysis is determining what those sine waves are for a given complicated wave. And then Fourier synthesis is just constructing a complicated wave given some series of sine waves. So these are just inverses of each other. Start with simple components, get a complicated waveform, or vice versa. Break up a waveform into simple components. All right. So here is what the Fourier series is. The problem with power series is that they're limited to certain continuous functions called analytic functions. But we need a type of expansion to handle periodic functions that may be discontinuous. You might think of the square wave. So what does a square wave look like? It looks like it goes up, stays constant, goes back down again, stays constant. It's discontinuous. There's a discontinuous jump. Step up, step down at certain discrete points. It's periodic, but it's discontinuous. You can't use a power series to approximate it. So, but you can use a Fourier series to approximate it, and that's what we're going to do. So here is the Fourier series expansion. Think now of a function of an angle. So eventually, theta here is just an angle. And f is going to be a function of an angle which is periodic with period 2 pi. So it's going to repeat itself every 2 pi. So in other words, this really, f of theta really only depends on the terminal side of theta. Bless you. Coterminal angles will give you the same value back. Okay. So here f is periodic with period 2 pi. I should probably just write that in. In other words, what it says is that f of theta plus 2 pi is always equal to f of theta. The function has to satisfy this for all theta. Then, here's what we can do. F of theta, we're going to write this as a double series. It's first we take some constant, which we'll call A naught divided by 2. So A naught is, if you like, the constant term in the series. And then what we do is we add cosines of multiples of theta. Cosine of theta, cosine of 2 theta, cosine of 3 theta, with certain coefficients, A1, A2, A3. And the coefficients vary depending on what F is. So, for example, if A1 is very large, and A2 and A3 and so forth are very small, then this function is going to look very much like cosine of theta, plus a constant. Okay. But if I've got non-zero A2, A3, then I've got some contributions of higher frequency terms here. Now, and so in general, the general term here is cosine n times theta, where n is some integer, at least 0, times some coefficient a sub n. But I'm not just going to add cosines, I have to include sine theta as well. So I have a whole nother parallel series down here, which I'm adding to this one, with other coefficients, b1, b2, b3, sine theta, sine theta. So I'm taking cosines of multiples of the angle and sines of multiples of the angle. Notice each term is periodic. So cosine of n theta satisfies this. If f is just cosine of n theta, then add 2 pi to theta, you're going to get the same value. Same with sine of n theta. So each one of these terms is periodic and satisfies the same equation that f does. So when you add them all up, you're going to get something that's periodic. So let's express this more compactly. I'll just leave the constant term out by itself, a naught over 2, and then I'll add from n equals 1 to infinity a sub n times cosine of n times theta plus b sub n times sine of n theta. So I've got two sets of coefficients. I've got the a's and I've got the b's. The a's and the b's are completely determined by the function f, uniquely. And conversely, if I know what all the a's and the b's are, of course, when I add them up, I get some unique function f when I do that, f of theta. So this is how we're going to decompose. Notice what these are. These are just simple sinusoidal functions. They just look like this. The cosines start at 0, up at 1, and go down, and then the sines start at 0 and go up. But other than that, they all look the same, roughly. But now, as n increases, these functions are going to oscillate more. They're going to oscillate more. Okay, in the same space. All right. So here, f of theta is a periodic function with period 2 pi. The constant term is a naught divided by 2. Why is it divided by 2? For technical reasons. The fundamental terms are the terms when n is equal to 1. So that's a1 times cosine of theta plus b1 times sine of theta. Those are the fundamental terms. The other terms are called the harmonic terms, for n equals, or also called the harmonics, for n equals 2, 3, and so forth. So the fundamental term is sometimes also called the first harmonic term, and this is the second harmonic term, third harmonic term, and so forth. Here are some discussion points. What's the difference between the Fourier series expansion and power series expansion? Just some obvious cosmetic differences. So, power series, the simple functions are powers of x. Those are not periodic. Those are simple functions. They're powers of x. Here, the simple functions we're using for the decomposition are the two principal trig functions, sine and cosine, of multiples of the angle. So that's one big difference there. The Fourier series works even for discontinuous functions. Whereas a power series can only give you a continuous function. But the Fourier series only works for a periodic function. So it could be discontinuous, but it has to be periodic. And in the case above, the period of this expansion is 2 pi. So every one of these terms has period 2 pi. It repeats itself after 2 pi. So the frequencies of the harmonic terms are integer multiples of the fundamental frequency also. So sine of theta, 2 theta, 3 theta. So there are no fractions. So they're just integer multiples. As opposed to powers of x, which are integer powers of x. All right. So let's get to an example here. So a typical discontinuous wave. So I'll just mention this, and then we'll analyze it after the break. It's called the sawtooth wave. And if you graph it, it looks like this. It's periodic, and it's discontinuous. So in the range from, say, minus pi to plus pi, so as x goes from minus pi to plus pi, this goes from negative 1 to 1, but it goes in a straight line. So, so if you want it in the range minus pi to pi, this function looks like theta divided by pi. So if theta is minus pi, you get minus 1 here. And if theta is plus pi, you get 1. And the value of the function is just linearly, varies linearly with theta. So it's a straight line with slope 1 over pi. And then but then it repeats itself. So from pi to 3 pi, it does the same thing. Or from minus 3 pi to minus pi, it does the same thing. So that's the sawtooth wave. And now, we'll take a break now. But when we come back, we are going to find the Fourier series for the sawtooth wave. And then what we're going to do is we're going to use the same thing we did with the power series. We're going to truncate the Fourier series to the first few finite terms and see an approximation, see what we get as an approximation to this thing. And then we're going to increase the number of terms in the approximation, and as we do that, we'll see that we get something that more closely resembles the sawtooth wave. So the same reason that power series are good for approximating a function, because you could just truncate it to the first few finite terms, doing that with the Fourier series is similarly good for approximating a periodic function that's discontinuous. All right, let's take 10, and then we'll come back to this.
What Thursday we're actually doing it. We're busy or not, or
If you do an angle, theta is fine. It's on Monday now.
Thursday.
Next Thursday.
Well, this Thursday. Because I know from what I saw on the calendar, it looked like it would be the only day before block two. I know I would like to. I don't know if anyone else would like
Continuous means that there are no breaks in the y values along the. If you have x and y, this function is continuous. But this function goes to here. That value is over there. This value really that's discontinuous. Right, so there's a break in that's what he's talking about, continuous versus discontinuous. say the power series works for continuous functions. 40A works for, can work for discontinuous, but it only works for periodic functions. Periodic functions are sine and cosine because they repeat.
So 4x is for
Periodic functions, but they don't have to be discontinuous. It can work for discontinuous functions. Like the sawtooth one is discontinuous.
right. That's
Yeah. Because it has that break right there.
a break.
But I believe the Fourier series also works for continuous periodic functions. The emphasis is on periodic. Make it through this, it'll be good.
Oh, I kind of. I forgot his name, but you said he was at Religious. And Mexico is
Your glasses.
Oh, yeah. But he said he was in Rock. He was in train on this. But he looks kind of young, but I think he's they had a reception for, maybe his chaplain at William Home, I mean, at Eisenhower, because they had a reception for Eisenhower.
I had this funny vision when you said about doing this in your sleep. Like literally like wake my wife up and doing this in my sleep, and she's like, I like it better when you were out in right there in Afghanistan. She's talking gibberish.
That's good. We only have like we only have like 3 more problems there. 1 more.
3 more points? Yeah.
3 more problems. That's good.
I don't like being dependent on chemical substance.
I go back to college, I remember how I was in college, coffee. I really did.
You didn't drink coffee?
No. I started drinking coffee after I joined the army.
I used to crush it up and snort it.
Into the army.
I probably would be dead right now if they had energy drinks when I was in college. I'm pretty sure.
I can tell you jumped on it really quick. It was literally a perfect usage, but well, it's not.
I don't remember having issues staying away from classes. I definitely did. Maybe I did all this time.
What's that?
See, right now, it's times like these that I'm missing the old red fuel and all that with the ephedrine in it. You know what I mean? The stuff they did. That shit got me confused.
Put that eraser in the fudge pan and see if it cuts it. This is like the same color almost. How pissed would you be if you stayed into the
This was somebody's God.
Remember when I got the personal white face? We were originally specifically for the next weekend. And then after 2 years, so that's a great idea.
Like, I will do that Wednesday afternoon.
Yeah.
Hey, we have no class, or we have class, but we have we're not having math on Thursday this week. How many people plan to take the Cisco exam?
Not this week.
Not this week.
What about next Thursday?
So I got 3, 4, not this, but okay. So before this week, I don't care if you plan to take it sometime in your life. It's on your fucking bucket list. All right, so 3. Okay.
I plan on taking it like sometime over Christmas break. Is that important? Relevant? Is that relevant to your question?
Sir, you asked. You're like, why don't we just say the answer to my mom? How about we do that?
Your mom's gonna take the CCNA test.
Maybe you.
Not with a voucher.
Yeah. She don't get a voucher.
Oh, yeah.
I'm including my lunch specifically on your mom.
They're taking it this way. I'm not worried, but dang it.
I probably want to take mine like the second half. Because the first half I English, there's plenty of stuff now.
I think I'm going to take mine. If there's a lot of dudes taking it this week, I'll go ahead and jump on the grenade. It's like,
You don't even know how that works.
we're not doing math on Friday, are we?
Yeah, we are.
No.
Yeah, we are.
We do math Friday? So we're not doing it Thursday or Friday. So our homework we get Wednesday, will we do Monday?
Yes.
I may do the Cisco on Thursday.
See, they're going to throw off the workout.
I might throw off a mojo.
All right. Good.
What are we doing Thursday and Friday?
Okay. So, sawtooth wave. So, keep this picture in mind because that's where we're headed. So the period of this wave is 2 pi. Okay, the period of its fundamental term is 2 pi also because it's just going to be sine or cosine of theta. Harmonics have higher frequency than the fundamental, but the entire series repeats every 2 pi radians. So here is the actual first 3 terms in the Fourier expansion of the sawtooth wave. So the fundamental contribution is from sine of x, or sine of theta, rather. So that's this blue curve. So it goes up, goes down, goes back up. I am my exam. Students are taking a final exam right now, so I might have to take this. Give me a second. Sorry.
Is there a difference between the word period and how it repeats?
Well, I may have misspoke. Actually, I didn't speak. We're having actual project management classes. I thought once the project management we were project management, but we'll have actual classes. But if you're going to take the test, you're just going to. I think the regular test times are 11 to 1 or whatever it is. So you'll just leave a little early and then come back when your mission complete. But those are things.
Are we getting our PIMP out of this?
Already got one.
So do we just need to go up there individually and schedule it with her?
What's
Yeah.
PIMP?
I think so.
Project management professional, I think so.
It's PMP.
It's PIMP.
We have to take a test on project management.
I don't know. Do we?
Not
Probably.
here.
I don't know.
I think the big one here.
PIMP? Like you're you guys are people.
I'm going to get my PMP certificate and draw an eye in it.
No, your certificate comes in grades on the pickup form.
It's actually just a purple fedora hat with a feather.
With a long hat, some yellow feathers sticking out.
Which one? Was that? Was that? So which was the
So the
one where
harmonica
they
would
had
be like
and it had the roots with the fish tank?
Let me just say,
Was that Hollywood Shuffle?
my students are taking a final exam from now until 11:30. They might call if they have a question, and that was what this call was about. I forgot to mention that right off the bat, but okay. So sorry for the interruption. So where were we? So the blue curve is the sine wave of fundamental frequency, and it is in fact sine of theta times some amplitude, which is given by this b sub 1, which is the coefficient. So this is sine of theta times b sub 1. That's the blue curve. Not saying what b sub 1 is yet. Then the next term in the Fourier expansion is sine of 2 theta, which is the green curve here. And notice it starts at the 0 point here. It goes down first. So its coefficient, B2, is actually negative. So it goes down this way. That's the green curve. And in absolute value, it has a smaller amplitude than the fundamental, you see. And in fact, these amplitudes have to diminish to 0 as n increases. The third term is sine of 3 theta, which is the red curve. It has positive amplitude again, B3. And that's that red curve. And it turns out that you might ask, well, what about the cosine theta terms? It turns out those are all 0. So all of the A coefficients, A0, A1, A2, A3, those are all 0 for this particular sawtooth line. And we only have the B terms. We only have the sine terms. All right. So since this repeats every period, we can get the entire behavior of the series just by studying one cycle. So we can limit ourselves to, say, one single period, say, from minus pi to pi. And then just look at that period because it repeats. So here is how we get these coefficients. Here's how we get these amplitudes for the various sine waves. So, and this is the Fourier theorem, which explains everything, which gives you the entire theorem. So a periodic function f with period 2 pi may be represented by a series of sines and cosines of the following form. So here's just repeating what we saw on the previous slide. Writing it like this. But now, the new part here is this tells you how to get the coefficients. So notice that these coefficients are expressed as definite integrals using the function. So for example, to get A0, which is the constant term that you divide by 2, you integrate the function f from minus pi to pi. And then you divide by pi. So really what this gives you is it sort of gives you the average value of f. You're summing up over f over period 2 pi, and then you divide by pi, but then you're going to divide by 2 again. So this constant term is actually the average value of f. It's the, if you like, it's the expected value of f. To get an for n greater than 0, you take f of theta times cosine of n times theta. Take that function and integrate it, again, over the period minus pi to pi. And likewise for Bn, take f of theta times sine of n theta and integrate that from minus pi to pi. And each case you divide by pi when you're done. Okay. The limits of integration here don't have to be minus pi and pi. The integration is over any period. Take one complete period of the function. So the space that you're integrating over has to have length 2 pi. But it can start anywhere and end anywhere. So you can go from 0 to 2 pi. Here, for the sawtooth, it's convenient to go from minus pi to pi because then the function just looks like a straight line in that period. Yes?
Does that have to be the same for each one? Does that have to be the same rate?
No. You could do for A0, you could do minus pi to pi, and then for A3, you could do 5 pi to 7 pi, or pi over 2 to 5 pi over 2. Yeah. No, completely independent. So in fact, if you vary the limits, at the same time, you increase them or decrease them by the same amount. For any of these integrals, the integral won't change. You get the same value. Okay. All right. So in the case of the sawtooth wave, to find the Fourier expansion, what we have to do is determine these coefficients in the Fourier series. So we have to do these integrals. We have to do these indefinite integrals. And at this point, we really only have enough to get the integral for the constant term. To get these other integrals down here, you need to do something like what's called integration by parts, which I haven't talked about. But we're not going to do that. This is a solved problem. So what we're going to do is basically go straight to the solution. And here it is. So for the sawtooth wave, we get this. We get A sub n. So this is again the Fourier series expansion. But now here, first of all, this first equation says, notice all the A terms have gone. All the cosine terms are gone. Like I said, all the A's are 0, including the constant term. So we're only left with the B terms, and I get sines of multiples of theta. And here are, in fact, the coefficients. So B1 is 2 over pi. B2 is negative 2 over 2 pi. B3 is positive 2 over 3 pi. And B4 is negative 2 over 4 pi. You can factor out a 2 over pi from the whole thing, and then the coefficients look a lot simpler. I get 1 minus a half, plus a third, minus a quarter, each one times the corresponding sign. Okay. Questions?
So, sir, the reason why you're not having to deal with any of this basically cosine in theta is because from the previous formula that you gave us, when you go from negative pi to pi, and you take that negative cosine value, and it's the other cosine value, those cosines are 0 at pi, or negative pi.
Not quite. It's not quite that simple because, that'll work because you're multiplying the cosines by theta. Remember, f of theta is theta over pi. So now you've got you don't just have a pure trig function here. You have cosine of, say, 3 theta times theta, which, when you integrate it, doesn't quite look just like a pure trig function anymore. But there is a point here, there is an easy way to see that these a's are 0. If f is an odd function, I'll write it this way. If f is odd, what that means is that f of minus theta is equal to minus f of theta. So if f is odd, then all the a's are 0. The sawtooth wave is odd. You take a minus angle, you're going to get minus the output. Okay. The reason for this is that So why do you get 0? Let's look at this. You're integrating from minus pi to pi, so you're taking the same amount on one side of 0 as on the other side of 0. So you take any odd function. Here's an odd function. And it's not quite odd. Well, okay. If I go from minus pi here to plus pi, I'm taking that integral. But notice that this area counts positively, that area counts negatively, and because the function is odd, those areas are equal, so they cancel completely. And I'm left with 0. Okay, so this integral, this area is equal to 0. That explains this first one. But now for these, f is an odd function and the cosine is an even function. Well, an odd function times an even function is an odd function. Easy to just check that. That's like a one-line check. Take an odd function, multiply it by an even function, you get an odd function. Well, that's an odd function, so it's also going to be 0. Now, the reasons these are not 0 is because the sine function is itself an odd function. And if you multiply an odd function times another odd function, what you get is an even function. So an even function is when you take the minus sign out and f of minus theta is equal to theta. Well, when you integrate an even function from minus pi to pi, you don't necessarily get 0. You could get anything. Okay? You can't say anything about what you get. But just by symmetry, because a sawtooth is an odd function, you are integrating odd functions here. And you're integrating them on, from one side of 0 to the other side of 0. The areas are going to cancel always. So that's why you get 0 for all of the a's. Let me go back. If f turned out to be an even function, then all these terms would be 0. All the b sub n's would be 0. So if f is even, then even times odd is odd. And you're left with integrating an odd function here, and so all the b sub n's are 0. And you're only left with a's. So it's purely cosines at that point. But for an odd function, you have only sines and no constant terms. All right. Okay, so that's why there are no cosine terms here. All the fundamental and all the harmonics are just sines. And notice the coefficients. If once you factor out 2 pi, I go 1 minus a half plus a third minus a quarter. That continues on. So the next one is plus a fifth minus a sixth and so forth. So they're the reciprocals of n, alternating plus and minus. All right. That's when you do those integrals by parts and you figure it all out. That's what you get. All right. So here is the actual curves you get by truncating this series for 2, 5, and 10 terms. So if you take 2 terms, so I'm going to go back, just take these first 2 terms and add them together and graph it. What do you get? You get this blue line, which already kind of looks a little sawtoothy. Well, if you take 5 terms, now you're taking, these 4 plus the next one. You get these squiggles here, but notice you're getting much closer to the sawtooth wave here. And then finally, with 10 terms, you're getting really close. So you get this big drop. This is a continuous function. But as you add more and more terms, this drop becomes more drastic, more precipitous. And in the limit, this is a discontinuous term. Okay, so you can see how truncating the Fourier series to just a finite number of terms gives you a fairly good approximation to the waveform.